All right, as promised, I have a couple of projectile motion problems for you guys. We're going to do two separate problems in two slightly different circumstances, and each problem will have multiple parts. So these should be some good examples for projectile motion problems, but do be aware your exam problems may not look exactly like this, and it's more important to focus on the concepts that are going to be presented here and the logic behind the series of steps than it is to memorize the math that I write down. So in this problem, we have a ball thrown horizontally with a speed of 15 meters per second from the top of a 9-meter tall cliff. So good to draw ourselves a picture over here. We've got our cliff, which is 9 meters tall. And the ball is given an initial velocity, VI, of 15 meters per second, and the ball's trajectory will look something like this parabolic arch there, where it strikes the ground below. And we want to know how far from the base of the cliff the ball lands and with what velocity it strikes the ground. So, first off, this is a projectile motion problem. We know because this ball is airborne, with no forces acting on it other than gravity, and we are ignoring air resistance for all of these problems. So knowing that it's a projectile motion problem, you know a few things. One, we're going to need a coordinate system. I'm going to use this coordinate system right here, with those arrows pointing in the positive directions for x and y. We also know we're going to need to label our initial and final points. So my initial point here is going to be the launch of the ball, and the final point is going to be here at the end of the trajectory when the ball lands. So for those initial and final points, we now need to take stock of what we have. So number one rule of projectile motion is keep your x and y variables separate. So automatically, it's a projectile motion problem, so we know our accelerations. AX is 0, and AY is 9.8 meters per second squared, directed downward, which in our coordinate system is negative. So after that, we can see what other information we have. Well, from the initial point to the final point, the ball moves down 9 meters. So that's our displacement in the y direction. The final height and the initial height are 9 meters different from each other, and the final height is lower than the initial height, so based on our coordinate system, that is negative. We've also been given the initial velocity, or the initial speed, and we need to figure out how this splits up into x and y. For this problem, the ball is thrown horizontally. And you can see that up here, the VI vector I've drawn straight to the right. When a vector is horizontal, that means its whole magnitude is in the x direction and there is nothing left for the y direction. So there's no triangle to write here. It's actually simpler than that. V initial in the y direction is 0 because something going horizontal has no y component. And then the initial velocity in the x direction, the whole vector goes in there, the whole magnitude. Positive 15 meters per second, positive based on our coordinate system. And I've called it VIX, but that's actually a little redundant, so I may as well just call it Vx, because the x velocity of an object will not change in projectile motion because the acceleration in the x direction is 0. So now let's start Part A. Well, we want the horizontal distance, so delta x is clearly the unknown we want here. So we can look through our x direction here and see what we have and what we don't. We have effectively VF and VI in the x direction. We have the acceleration. We're looking for delta x. And in the x direction, we really only have one equation anyway. So delta x equals VIT plus 1/2 AT squared. And that's what would be on your formula sheet. And to turn that into an equation for just the x direction, well, we want to delta x for sure. Vi, we just want in the x direction. And again, the initial and final velocities are always the same in the x direction. So we can just call that Vx times t. And this other piece disappears because the acceleration in the x direction is 0. So we could find delta x, which is what we really want here, but we need t first. So to find t, we can go into the y direction. In the y direction, we have a delta y and VIY, and we're looking for t. So the equation we need, as it appears on your formula sheet, would be delta x equals VIT plus 1/2 AT squared. And we want to make that into a y direction equation. So delta y instead, not just the initial velocity, but the initial velocity in the y direction. Time stays the same, plus 1/2 times acceleration in the y direction times time squared. The only variable we don't know in this equation is time, so we can just solve for it directly. Plug in the -9 meters for delta y, 0 for the initial velocity in the y direction, so that whole term is 0, plus 1/2 times -9.8 meters per second squared times t squared. So we have used the quadratic kinematic equation, but because the term with the t disappeared, we won't have to actually use the quadratic equation. So moving this all around and solving for what we need, we find that t equals 1.36 seconds. And actually, since we have to take the square root to find this answer, we have to decide whether we want the positive or negative time. And we definitely want the positive time here. So now we have t. So let's go back and plug into that x direction equation to find our answer. I'm going to move the rest of my solution up here. But delta x is velocity in the x direction. That's the positive 15 meters per second, times the time of 1.36 seconds. So our delta x has a final value of 20.3 meters, meaning the ball lands 20.3 meters from the edge of the cliff, and this right here on our diagram is our delta x. So that is part A. Then for part B, let's switch to a different color here. Now we want to know the velocity when the ball strikes the ground. Oh, before we go on, I just wanted to point out that for this problem, it was the y direction that found us the time. And something will be a little different in the next problem. So here, the reason the y direction found us the time is because you hit the ground at the end of your flight path here. So it's your y coordinate that can't get any smaller. So as soon as y gets down here to y equals 0, then the flight stops. So y is limiting the time of our flight, so the y direction finds us the time. You don't actually need to be able to figure that out yourself. If you try the x direction and it doesn't work, just try the y direction instead. Anyway, back to part B. We want to find the velocity with which the ball strikes the ground. So for velocity, we're going to want the magnitude and the direction. And there are only 4 things you can know about any vector. So if we want the magnitude and direction of VF, we're going to need to find the x and y components of VF. One of these is very easy. VF in the x direction, well, there is no initial and final in the x direction because the x acceleration is 0. So our VFX is still that positive 15 meters per second. Now we need VFY as well. So one more time showing you guys how this works. On your equation sheet, this is the equation that you'll see. And to make that into a y direction equation, we want the final velocity in the y direction squared equals the initial velocity in the y direction squared plus 2 times the acceleration in the y direction times the displacement in the y direction. We already have a lot of these variables. VFY is our unknown, that's what we're trying to find. VIY was 0. Plus 2 times the negative 9.8 meters per second squared of our acceleration in the y direction times our negative 9 meters is our y displacement. If you end up having to take the square root of a negative number to get your answer, you've probably lost a negative sign somewhere. Go back and look for it. But we have to take a square root here, taking the square root of both sides of this equation. So when you take a square root, you decide whether it should be positive or negative. The number we get out of here is 13.3 meters per second, and we expect this ball will be traveling downward. Getting a little messy up there, but there's the vector that corresponds to VF. So if the ball is traveling downward, that's going to be our negative y direction, and again, we decide that negative sign there. Now we have the x and the y components, and things get hopefully nice and easy from here. To draw our vector, I'm going to draw my x component first. Vx is positive 15 meters per second. I'm actually going to drop the positive and negative here because I drew Vx to the right in the positive x direction, so I've already accounted for that positive or negative sign. Same thing with VFY. I'm going to draw it pointing down because of the negative sign, and then I'm just going to label this side as regular road 13.3 meters per second. Already accounted for the direction. Don't need that negative anymore. So here is VF. There's your right angle, and here's the angle we're going to end up finding. To find the magnitude, we're just going to use our old friend, the Pythagorean theorem. So V final in the x direction squared plus V final in the y direction squared, square root of all of that. So that's the square root of 15 meters per second, quantity squared, plus negative 13.3 meters per second, quantity squared. That negative, it actually wouldn't matter if you leave it off because you're squaring the negative 2, so it's going to go away. And, well, we just took a square root, but magnitudes are always positive, so we know we want just regular old 20 meters per second. In general, you don't want to put a positive or a negative sign on a magnitude. Just leave it how it is, assumed to be positive. Then last but not least, we have this angle theta, which is going to be the inverse tangent of VFY over VFX for this problem. If you don't see where that comes from, go back and watch the trig video again. But that angle, or those numbers, so you can see where they go, 13.3 meters per second divided by 15 meters per second. The units of those numbers have been made clear over here already, so I'm going to drop them for that step. And we get theta is 41.6 degrees. All angles need a reference. And for projectile motion, it's usually easier to say above or below the horizontal. And for this problem, that is 41.6 degrees below the horizontal. So again, we have a reference. The horizontal is our reference. That's this line up here along which Vx lies, and we're measuring our angle down or below that line. So this is this entire problem. It's got some good pieces in here. It's got recognizing what a horizontal vector means. It's got using an x direction equation, or rather using a y equation to find a variable you need, time, to use in an x equation to get your answer. And it's got our standard vector stuff, where we're finding the two components and knowing we need to find those two components, then combining them into the magnitude and direction that we need. So now let's move on to the second problem. Again, we're going to continue this fascination with cannons that I seem to have, and we're going to fire a small cannon from the base of a cliff, fire a cannonball with a speed of 27 meters per second at an angle of 40 degrees above the horizontal. And if the cannon is 45 meters horizontally away from the base of the cliff and the cliff is 12 meters tall, we want to know by how much vertically does the ball clear the edge of the cliff, how much time passes between the ball passing the edge of the cliff and the ball landing, and again, what's the velocity of the ball as it lands. Once again, this is a projectile motion problem, so I will need a coordinate system, and I'm just going to go ahead and choose that right now. Put it up over here. You need to label your x and your y on your coordinate system. Can't just draw that little symbol. You need to figure out which one's positive x and which one's positive y. Also, north, south, east, and west, while a useful way to describe the direction of something, doesn't tell you what positive y and positive x are, so you still need to label your y and your x on these coordinate systems. Again, a picture is a good idea, and with my amazing ability to draw perfectly straight lines, let me try that again. Not to scale. We have a small cannon down here that's going to fire the cannonball with our initial speed of 27 meters per second at an angle of 40 degrees above the horizontal. So there's the above, and the horizontal is our reference line. And that ball's flight path, let's pick a slightly different color here. It's going to go something like this, but more looking like an actual parabola. So give me just a second here. Maybe if I do it from the end. There we go. Close enough. But let's see if there anything else we can label here. We know the distance to the edge of the cliff. This is that 45 meters. And we know the height of the cliff. That's this distance right here, 12 meters. So that seems to be everything we need so far. And now we're going to move on to thinking about part A specifically. So part A I'm going to do in blue. And for part A, we're going to need to choose initial and final points. So we know a lot about the launch. We know all of our speeds and angles and things there. So the launch is a good place to choose as our initial point because we know a lot of information about that point right there. And then we want to know by how far vertically, this distance right here, the ball passes the edge of the cliff. So if we want information about this point, we need to make that point either initial or final. So part A, all of the math, is only going to be referring to this blue portion of the trajectory. A reminder that my drawing is not necessarily to scale. That will come into play here soon. But back to blue and back to part A. We want to start thinking about the different variables that we have, again, in X and Y. And It's a projectile motion problem because the cannonball is in the air only under the influence of gravity, ignoring air resistance. And when it's a projectile motion problem, you know your accelerations. Again, I've chosen up to be positive y, so my acceleration is negative 9.8 meters per second squared. And there's a few other things we know. From our initial to our final point, our delta x is going to be positive 45 meters. Delta y is not going to be exactly what we need, but we're going to need to find it first before we can find our answer. And we know a little bit about our velocity. Our initial velocity vector that I'm going to, still in blue over here, points like this with a magnitude of 27 meters per second, and it will have an x component and a y component. So that's VIY, and this would be VIX or just VX because the x velocity does not change. And we know this angle down here is our 40 degrees. So doing a little bit of SOHCAHTOA, we can find that our velocity in the x direction is going to be 27 meters per second, and we want the adjacent component, so that's times the cosine of 40 degrees. And this should be positive because Vx points to the right. So we get a Vx of positive 20.7 meters per second. We can do the same thing with our y direction, VIY. Again, it's going to be positive, and it's going to be the magnitude times the opposite component, which goes with the sine of theta, which gives us a number of positive 17.4 meters per second. So this time skipping over the step where I take the formula sheet equation and convert it into an x or y equation, I'm going to write a y equation that might help me find my final answer. Delta y equals VIT plus 1/2 AY t squared. From this, I could find delta y, but first, I need my t. So this time, the y direction can't find us our time. We're going to need to look in the x direction instead. It's because this final point up here, it's not when the ball hits some y coordinate that it stops, the little timer we have going here. We want to know what happens when it passes this x coordinate. So that means that x is going to limit our time in this problem. So going to the x direction now. Wish I could stop it from doing that. I don't know what makes that happen. Anyway, pulling out basically the only x direction equation we have, delta x equals Vx times t, where we know delta x is 45 meters. We know Vx is positive 20.7 meters per second. Delta x is positive as well, times t, which gives us a time of 2.17 seconds for the blue part of the flight. Now we can put that 2.17 seconds up into the equation that we had from before. So delta y is VIY, positive 17.4 meters per second, times the time, 2.17 seconds, plus 1/2 acceleration in the y direction, negative 9.8 meters per second squared, times t squared. 2.17 seconds, whole thing squared. And this works out to be delta y is 14.7 meters positive. Always stop and ask yourself when you calculate a number from an equation after a lot of math, is this number what the problem asked for? And we want to know by how far vertically does the ball clear the edge of the cliff. But what we just found was our whole delta y, from our initial point all the way up to our final point. So clearly we can see that the number we need is really going to be our answer, 14.7 meters, minus the height of the cliff, which gives us the ball clearing the top of the cliff by 2.7 meters for part A. I'm going to move on to, we'll say green for part B. And I will start up here. Draw ourselves a little separating line. So this time we want to know how much time passes between the ball passing the edge of the cliff, that happens right here, and the ball landing on the top of the cliff. So now we're looking at this portion of the flight right here. So what used to be our final point is now our initial point, and we have a brand new final point. So this means some of our variables can be reused and some of them cannot. So our accelerations in the x and y direction are going to stay the same because they always do in projectile motion problems. And let's see, what else? Our x velocity does not change for any part of the flight, so that 20.7 meters per second is still good to go. The amount of time for the green portion of the flight isn't going to be the same as the amount of time for the blue portion of the flight, so we cannot reuse our time. Our initial velocity from before was down here at the launch point, but delta y, we can't reuse, but we can figure it out. So we started at 14.7 meters above the ground, and we land at 12 meters above the ground. So our delta y here, the change in height for that green portion of the flight, is 2.7 meters in the downward direction. So the negative on there. Well, we're going to need some more information here to answer our question, either an x distance or one more piece of information in the y direction. And it's actually v initial in the y direction that we can find, because v initial for the green part is the same thing as v final for the blue part. So if we go back into our blue numbers over here, we could use vfy equals viy plus ay times t to find the final velocity for the blue section, which is the same as the initial velocity for the green section. So vi in the y direction was that positive 17.4 meters per second plus negative 9.8 meters per second squared times the time, again from the blue part, so we want that 2.17 seconds again. And we get VFY equals negative 3.87 meters per second. And like we said, that VFY from before is our VIY now. There are a couple things that I did here that I want to point out to you guys. One, I chose not to use the equation with the VF squared equals VI squared because I'm not really sure whether the ball will be traveling up at this point or traveling down at this point. So I wouldn't know whether to assign it a positive or negative value, and that could have a big effect on the numbers I calculate. So I chose to use this equation instead because, the equation will just tell you whether the value is positive or negative. Also, to come back to my drawing not being to scale, based on my drawing, it kind of looks like this point might be the peak of the ball's trajectory. But that's just because of my random estimation guess that I made when drawing this picture. The ball may have reached its peak before the edge of the cliff, it might reach its peak after the edge of the cliff. We could do a calculation to find out, but we just aren't sure. So don't assume unless you know for sure. Now we have A in the y direction, we have delta y, we have VIY, and we want t. So we can use the quadratic kinematic equation. Delta y equals VIYT plus 1/2 AY t squared. And plugging in our values looks like this. So here's that negative 3.87 meters per second times t plus 1/2 times negative 9.8 meters per second squared times t squared. Now we have some numbers with no t's, some numbers with t's, and some numbers with t squareds. This is a quadratic equation, and we need to use our quadratic formula. So the first step in any quadratic equation problem is move everything to one side of the equation. You will get the wrong numbers if you don't. So I'm going to move everything over to the right and drop my units here for now, rearrange the equation a little bit. Negative 4.9 t squared, that's the half times the negative 9.8, minus 3.87 t plus 2.7. Now in terms of our quadratic equation, our A is going to be this negative 4.9. Yes, you need to keep that negative. B is going to be negative 3.87. And C is going to be positive 2.7. Now I'm not going to show all the details of how to actually plug this into the quadratic formula. There's another video from that. You can go check it out. But we get two answers out of our quadratic formula. Negative 1.24 seconds and positive 0.45 seconds. And what we want here is the positive time, and in general, if one of the answers is negative, you're just not going to choose that one. So now we've got the time that Part B asked for. Part C I'm going to do in red. And let's get ourselves another little dividing line here. So always thinking about our initial and final points, we want to know the velocity of the ball as it lands. So that's right down here where the ball lands. So if we want to, we may as well just put our initial and final points at the same place as we had them for Part B. We could also put our initial point at the launch and then do things like say the time for the whole flight is 2.17 seconds plus the 0.45 seconds from the first part, and so on and so forth. But for this one, it's probably easiest just to pick the same ones from Part B. So to find the velocity of the ball as it lands, if we need the magnitude and direction, or rather, sorry, if we want the magnitude and direction, that means we are going to need the x and y components. Just like way back at the beginning of the problem when we broke VI for the blue section down into its components, we wanted x and y, so we needed or reused the magnitude and the direction to find it. But over here, we're going to need our x and y components, and again, Vx never changes because the acceleration in the x direction is 0. Vx, the final x, is positive 20.7 meters per second. And then we need Vfy, so we could use a bunch of different equations here, but I'm going to use the Vfy squared equals VIY squared plus 2AY delta y formula. And we have Vfy squared equals V initial in the y direction, same initial and final from part B, so we can use that negative 3.87 meters per second, that whole quantity squared, plus 2 times the acceleration we always use in the y direction for these problems, times delta y, which again we can reuse from part B because we have not moved our initial or final points. And the ball will clearly be traveling down at the end of this flight path. I'll draw that vector in orange. It's going to overlap some other stuff. But there is the velocity of the ball as it lands that we're finding. The y component is clearly negative. So when we take the square root here, we're going to take the negative option, which turns out to be negative 8.24 meters per second, where we chose that negative. Now we have the x and y components, so we do our vector stuff to put them together. I'm going to draw my vector first. First we have v final in the x direction, which points to the right because it's positive. And when we draw our triangles, we take the positive or negative into account by the direction we draw the arrows, and then each side is just given a number. And then the y direction points down for this problem. VFY is downward, and I'm going to just record a regular old 8.24 meters per second here. I'm accounting for this negative sign by drawing that vector pointing downward, which means this is my whole final velocity vector, and that's the angle I'm going to find. So again, the magnitude of the final velocity, the magnitude of any vector really, will be square root of its x component squared plus its y component squared, which for this problem is, dropping my units, 20.7 meters per second squared plus 8.24 meters per second squared. Technically VFY is negative, but we would lose that negative when we squared that number anyway. So we get a magnitude of 22.3 meters per second. But that's not all that was asked for, because they asked for the velocity. And velocity is a speed, which we just found, and a direction. I'm just about out of room here, but theta is the inverse tangent of our y component, that 8.24, divided by our x component, 20.7. Notice I have dropped my positives and negatives here. I already accounted for them by the direction I drew those vectors. Then do the inverse tangent, and we get 21.7 degrees. All angles need a reference, so the easiest one for this is probably below the horizontal. Almost ran out of room there. And that's the answer to part C. So these are two pretty good problems to look for. A good example of using the y direction to find the time to answer an x variable, and using the x direction to find the time to ultimately determine a y variable. Good examples of moving our initial and final points. Good examples of vectors that are horizontal versus vectors that have x and y components. Good examples of combining our components back together to find a whole vector and its direction. Just about every tool you could use, every trick you could use is here somewhere. The trick is figuring out which ones to use when. But always keep your x and y variables separate. Choose your equations carefully. Be conscious of your initial and final points and where they are. When you move your initial and final points, be aware of that and think carefully about which variables you can reuse. And always choose a coordinate system, and do make sure you use your coordinate system as well. It's not enough to just draw that symbol in the corner of the paper. You need to actually include positives and negatives on your answers as well. All right, that is all for today, and I will see you all in class and in workshop.